Hey everybody, it's Ripley back again. Oh man, we're in the last couple sections of this entire course, which is pretty cool. They get a little beefy, don't be afraid, but they are super fun. We're going to talk today about representing a function as a power series. Now remember, a power series is any series of the form c sub n times x minus a to the n, and where n goes from either 0 or 1 or 15,000 or who cares, right? Let's go 0 to infinity. All right, now, by and large, as you probably already realize, usually these guys are going to look mostly like something like this, all right? And goes from 0 to infinity. They're usually centered at 0, but not always. This is centered at a. This is centered at 0. It doesn't really matter. All right. So what I'm going to do is I'm going to take some functions, and I'm going to turn them into power series. And you're like, Ripley, how is that at all possible? Well, the whole thing has to do with geometric series, believe it or not. In this section, I will teach you how to turn any function into a power series in the next section when we start talking about Taylor polynomials. But for now, we're just going to deal with representing functions as power series using the geometric series sum as a conduit through which everything passes. So if you recall, if I go a times r to the n, remember what this looks like. This is a plus ar plus ar squared plus ar cubed plus dot 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 plus ar to the n plus dot dot dot, right? This is called the geometric series. Cool thing about the geometric series is that we know that it sums to a over 1 minus r, which is awesome. Okay, now watch this. I'm going to take a real simple function like 1 over 1 minus x. Now, do you see how similar these things are? They are, if you think about it, excuse me, for this equation right here, do you agree, excuse me, that a would equal 1 and r would equal x? True? Now, all I'm doing is just looking at the form, which implies that since these two are basically the same with values filled in for a and r, that I can rewrite this function as the sum, as n goes from 0 to infinity, of a, which is 1, times x to the n. Now you may ask yourself, Ripley, wait a second here. You're telling me that, let's go through a few of the iterations, a few of the terms. When n equals 0, I get 1. When n equals 1, I get x. When n equals 2, I get x squared plus x cubed plus dot 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 plus x to the n plus dot dot dot. Goes forever, right? And you may be saying, Ripley, there is no way that this function and this function are the same. In fact, I'm going to bring up the graphing calculator in a second here and we'll look at it. We got to be careful. Remember, for a geometric series to converge, we know that absolute r has got to be less than 1, right? In other words, r is between -1 and 1. So if we're going to use the geometric series to sort of anchor this function, then we know that this function equals this series if and only if absolute x is less than 1. In other words, if x is between -1 and 1. All right, now look close. Don't take my word for it. Let's look close. Because remember, this function is defined for all real values except x equals 1. This series will only converge to this function when I'm between -1 and 1. So if you don't believe me, let's check it out. Let me bring up the TI really quickly. I probably should have brought this up earlier, but that's okay. I'm going to graph the two functions, all right? And I'm going to show you something. So sorry, waiting. Nope, I don't want to know. All right, so y equals, I need to be in a different mode. Let's go down to functional mode. It's always good to run through these things. Hit enter. I could tell that because it was in T, because we were in parametrics before, if you recall. So y equals, and then what I do, 1 divided by, got to use parentheses, otherwise it'll use order of operations and screw me up. And paren, let's just go zoom standard, which is zoom 6, and we'll just take a gander at it. Boom, we know that it looks like that. Right? Nothing to it. Now, what I'm going to do is I'm going to graph. I'm going to mess with the window a little bit, but I'll do that in a sec. Let's go back to this. I'm going to go down, and I'm going to go 1 plus x. And then I'm going to graph it. So we get that, and we got it. Okay. Well, at least we know it's, remember, if I go back here, since I'm calling this a power series, I'm calling this a power series. Let me change colors just so I can highlight some stuff. This thing is centered at 0. So at least we know based on the grapher that at 0 they have the same value, right? 1. No doubt about it. Okay, thank God. Or, yeah, exactly. So, you may say, wait a second, Ripley, how do they have 1? Well, because if I plug zeros in for x's, I end up with 1. I don't know why it's doing that. Stop it. Go away. All right, back to my TI. Let's see what happens. I'm going to add some terms, and we'll see if this starts to look similar. So over, and I'm going to go plus x squared plus x cubed. Let's go out to the 5th. Plus x to the 4th plus x to the 5th. And then what I'm going to do is I'm going to zoom in. I'm going to mess with my window. I'm going to make my window, my x value, I want to go from instead, instead of negative 10 to 10, I'm going to go from negative 1 to 1 because that's our interval of convergence. We know that because it's a geometric series. Let's graph it. So here comes the first one. Whoa, that's crazy. Look at that. They're getting really, really close to one another. Isn't that insane? Now, let's do it again. I wish I had different colors. It'd be awesome if I had different colors. I guess I could get that with a new upgrade, but we'll see. We'll see. Let's go over. I'm going to go 3 more terms. Let's go out to, where am I, at the 5th or the 4th? So we'll go out 6th, 7th, 8th, and we'll see what happens. Come on, what's going on here? Ah, 5th. Sweet. Okay, plus x to the 6th plus x to the 7th. I'm not missing anything, right? Plus, whoops, nope, delete. There we go. Plus x to the 8th. Now let's graph it, see what happens. Okay, there's the original function. Holy smokes, now we're just missing a little bit here. And then let's see what happens. Still grinding. Oh, and a little bit here. Look at that. But remember, before, this thing started to diverge from the function a little bit further back. And what we're doing is we're sealing. If we let this thing go to infinity, these two curves would match perfectly. Perfectly. Oh, I do want to show you something. Let me go. Let's go. And this is gonna drive you crazy. I want to show you how it diverges if I stop. Instead of stopping at x to the 8th, come on, go, go, go. Instead of stopping at x to the 8th, so one downside of this application is, let's stop at x to the 7th and see what happens. Or let's just add one more term. We'll go out to x to the 9th, and you'll see how it diverges. Because it can diverge ugly. I'm not saying it's got to be absolutely beautiful. Come on. Where are we? 7. Sorry, I should have cooking showed this, but you know me. I'm crazy. All right, let's go plus x to the 9th. And I'm up there. Come on, over plus x to the 9th. Let's graph it. Watch this. Boom. And then we're super close over here on the left. Up, up, up we go. Up. And watch what happens. It's going to go wha-bam down here because it's a cubic. Watch. Oh, actually it's not because it'll go wha-bam later on down the road. But I did get a little bit closer. So sometimes what will happen, depending on the behavior of the function, of the power series function, what will happen is you'll get a divergence where this curve will come up and then go wha-bam and it'll drop off. In this case, the behavior, because think about x to the 9th behaves very much like an x cubed, right? Or you might have that thing drop off this way or take off this way. It's okay. That's okay. We know if we let n go to infinity, we get the exact same curve, which is pretty freaking magical if you think about it. All right. Now, how about this guy? What if I wanted to do let's do f of x. Oh, I can't do that. I'm sorry, you guys. I cannot do this whole thing in red. It's going to make my eyes hurt. Let's do f of x equals 1 over 1 plus x squared. How about that? But Ripley, whatever will I do? It doesn't look like this beautiful geometric series. Well, it kind of does, doesn't it? Can I write this as 1 over 1 minus negative x squared? Aren't they identical? In which case, what's s? Well, s is going to equal what? It's going to be the top, which is 1, right? It's the first term, a over 1 minus r, right? And then what is, I've got 1 minus negative x squared written like this, which implies that a equals 1 and r is equal to x squared, right? Well, negative x squared, excuse me. That guy right there. I don't know why I put parentheses there, but I wanted to make sure that you saw that. What you don't want to do is negative x squared, because that's not what it is. And that's important because when I write the series, what happens? I get the sum as n goes from 0 to infinity of 1. I'm not going to write that. That's insulting. Negative x squared to the n. How's this written? Well, this is written as a sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n. Hey, guess what? I have an alternating series. Oh, isn't that amazing? So this function, tau, is written as this series, tau. Now we better let's find the radius of convergence, right? Let's find the interval of convergence. Well, this series is centered at 0 because otherwise it would have an x minus a to the n, right? So I know that absolute x squared has to be less than 1 because the geometric series tells us that, right? Well, if absolute x squared has to be less than 1, then clearly absolute x has to be less than 1, doesn't it? True, which implies that x is between negative 1 and 1 again. And if I graphed these, then guess what would happen if I graphed this guy, which hopefully you know what this looks like. Remember, this kind of looks like a bell-shaped curve. It looks like that. If I graphed this and then a couple of iterations of this, what would I have? Well, let's graph it. What the heck? Let's go back here. Clear, and this is going to be 1 divided by 1 plus, and we're going to go x squared in and then let's get rid of this guy, and we're going to clear. Now, we've got the same radius. You got to be careful. That's not always going to be the case. That only worked out because we had absolute x or absolute x squared. Now watch, I'm going to graph this thing from negative 1 to 1. Let's back up. Let's go zoom. Let's go window. I need to make this a little more interesting. Instead of y max is 10, let's go y max is 1.5. That'll be easier. 1.5. And now we should be able to graph it a little. Whoa! Oh, yuck. Let's try this again. Let's go window. I'm going to make y min equal to, let's make it equal to 0, because we know that it's always positive, right? Make that sucker 0, and I'm going to go, let's go negative 5 to 5. Sorry guys, negative 5 to 5. And we should get that nice little bell-shaped curve. Oh, bam. Oh, so beautiful. All right, now let's go back here and let's graph a couple. Okay, recall it's negative 1 to the n, x to the 2n. So when n equals 0, I get a 1. Then I'm going to have a minus when n equals 1, because negative 1 to the 1 is negative, right? So I'll have a minus, and then what'll I have? Well, I'll have a minus x squared, right? So this is going to be x squared. And I'm going to have a plus, because negative 1 squared is positive. When n is 2, I'll get x to the 4th. So I got to go x to the 4th. And then I cruise over. And then I'm going to have a minus, what? Well, x to the, when n is 3, I get a negative. And this is going to be x to the 2n. Is going to be x to the 6th. And then I cruise over. Let's do 2 more. Plus, what is this? X to the 8th, right? X to the 8th. And then minus x to the 10th. X to the 10th. Over and graph the two at the same time. So there's the original. Here's the new one. Now look. So this, did you see what just happened here? Remember, the radius of convergence is negative 1 to 1. So let's go back to our window really quickly and go negative 1 and 1, because that's our radius of convergence. And the graph. Here's the first function. Wow. Look at that. It's beautiful, isn't it? It's almost perfect. And then it starts to miss. Well, why does it start to miss? Because I haven't gone out to infinity. That's amazing. That to me is just straight up magic. I love it. Okay, so as opposed to last section where I got interrupted 19 times, I'm going to go ahead and I'm going to stop the video now. Oops. I'm going to go ahead. What are you doing, Ripley? I'm going to go ahead and I'm going to stop the video now, and I will get back to go away. And I'll get back to, meet you guys back here at my next break. All right, have a fabulous day, and I'll see you in the next section. All right, so I'm back. Sorry about that, you guys. So I know that I can write, let's pop over here real quick. I know that I can write f of x equals 1 over 1 plus x squared now as the sum, as n goes from 0 to infinity, of negative 1 to the n x to the 2n, right? Now, watch this. This is the coolest part. Remember, there's a rule that says if I have a sum of a constant times a sub n, this can be written as the constant times the sum of a sub n, and in reverse, right? This is like a hammer. It works both ways. This constant, as long as this sum sees a constant, I can either pop it out or just put it into the sum. For example, what if I let g of x equal x over 1 plus x squared? Now, we got to kind of look at this because this would still work as a geometric series, but it's far easier to look at this as x times 1 over 1 plus x squared, right? Isn't this just x times 1 over 1 plus x squared, which is just x times the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n, which is equal to the sum, remember, by this rule right here. Now, you may say, wait a second, Ripley, that's not a constant. Well, yes, it is. As far as this series is concerned, anything that is not an n is a constant, so I can stuff it inside. So this can be rewritten as the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n, plus 1. Now, let's check something. Let's make sure I'm not lying. Remember also that this could be written as x over 1 minus negative x squared, right? Now, this is in the geometric setup, as it were. Look at it. It's beautiful. Sitting there just like it should. Remember, if I think of this as a over 1 minus r, right? Then we know that a is equal to x and r is equal to negative x squared. So this is equal to the sum. This is equal to the sum as n goes from 0 to infinity of a, which is x, times negative x squared to the n. And guess what? We end up, after doing a little bit of algebra, right? Pull the negative out, I end up with exactly the same thing, which is awesome, right? This function is this series. Holy smokes. Well, your spidey sense may already be tingling because you're looking at 1 over 1 plus x squared, which we know is what? Don't I know that the derivative of inverse tan of x is equal to what? 1 over 1 plus x squared. True? So think about this. If this is equal to the sum of infinity, negative 1 to the n times x to the 2n, then how can I get back to inverse tan? Well, for example, if h of x were inverse tan of x. Now, in this case, we are totally screwed as far as it looks nothing like the geometric setting, right? If I call the geometric setting the a over 1 minus r, it looks nothing like it, all right? However, I can get there because what else do I know? I know that the integral of a sum is the sum of the integral. So inverse tan is equal to the integral of the derivative of inverse tan of x, right? Everybody agrees with that? That's a no-brainer. Well, that means that this is equal to the integral of 1 over 1 plus x squared dx, which is also equal to the integral of the sum, as n goes from 0 to infinity, of negative 1 to the n, x to the 2n, dx. The integral of the sum is the sum of the integral. So I've got, this now becomes the sum of the integral of negative 1 to the n, x to the 2n, dx. Now, right now your mind may be a little bit blown, but just sit with it for a sec. If I know that this thing right here equals this thing right here, and I know that the antiderivative of this is the inverse tan, then the antiderivative of this is also equal to the inverse tan, right? So let's just do it. Now, don't be afraid of the negative 1 to the n. Remember, that's an x. This is where it can get confusing. You got to keep your brain straight as far as dealing with n's or dealing with x's. As far as the as far as the integral is concerned, x is the variable, n is the constant. As far as the sum is concerned, n is the variable, and x is the constant. So that can get a little bit confusing, but it just takes a little bit of practice. So this becomes the sum, as n goes from 0 to infinity, negative 1 to the n, that's just a constant, it's along for the ride, x to the 2n plus 1, right? The antiderivative of x to the 2n is x to the 2n plus 1 divided by 2n plus 1. Now, there's a plus c here. All right? And you may be going, oh, goodness, Ripley, how am I going to deal with this plus c? This looks horrible. Well, it's really not that bad. Remember, this whole thing is supposed to equal the inverse tan of x. So if only I had a value that I could plug in that were delightful. Well, what do we know that the inverse tan of x is? Or excuse me, not of x. What a moron. You just solved for that, Ripley. What do we know the inverse tan of 0 is? Well, the inverse tan of 0 is equal to 0, which is equal to the sum, as n goes from 0 to infinity, of negative 1 to the n, 0 to the 2n plus 1 over 2n plus 1, right? Plus c. Well, thank God, 0 to the anything is 0, as long as it's not infinity, right? And this equals 0. So this implies, since this guy is 0 and the whole thing equals 0, this implies that c equals 0, which is powerful good because it just gave us inverse tan of x, which is equal to the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Now, you may say, but Ripley, that's a power series. Why, yes, it is a power series. You would be correct. Excuse me. Where is that power series centered, Ripley? Well, it's centered at 0, right? Because x, remember, power series, x minus a to the n, where a is the center. This is x minus 0 to the 2n plus 1. We don't care that these things are not equal here. They function the same way. Excuse me, I got to get a drink. I'm parched. Pardon me, sorry about that. So you may say, well, what was the radius of convergence? Well, we knew that the radius of convergence for this, we knew that absolute x had to be less than 1. Here's the coolest part. The radius of convergence for the integral of the same series, right, is exactly the same radius. In other words, radii are preserved whether I'm taking an integral, spidey sense is probably tingling a little bit here, or a derivative, right? So in this case, absolute x has got to be less than 1. Now, there's something that I want to get you in the habit of thinking about, though. All right? I want you to think, because some strange stuff can happen with these from time to time, just saying, check your endpoints. If you've taken a derivative or if you've taken an antiderivative, always think about checking your endpoints really quickly. So, for example, if I were to put in, let's see, if I were to put in 1, do you agree that, now I'm checking my endpoints in the series, so let x equal 1, which is an endpoint of that interval. Well, what happens when x equals 1? This becomes the sum as n goes from 0 to infinity of negative 1 to the n over 2n plus 1, doesn't it? Because 1 to the anything is 1, right? Pardon me. So what does this thing do? Does it converge or does it diverge? Hey, guess what? It converges. Why does it converge? By alternating series test. So we just picked up 1. Now what about let x equal negative 1? Well, if x equals negative 1, what happens? Now this guy's a little bit trickier. I'm going to write this one out. This is going to be negative 1 to the n. Negative 1 to the 2n. Now I'm going to go times negative 1. And this is all going to be over 2n plus 1. Because negative 1 to the 2n plus 1 is negative 1 to the 2n times negative 1, right? So let's see what happens. This whole thing ends up turning into what? Well, I'm sorry, I got to clean this thing up a little bit. This becomes the sum, as n goes from 0 to infinity, of, well, negative 1 to the 2n, excuse me, is what? That's just going to be 1 always, isn't it? Because it's negative 1 squared and then raised to the n. Well, negative 1 squared is 1, so we don't really have to worry about that. So this becomes negative 1 to the n plus 1 over 2n plus 1, doesn't it? Which does what? Hey, guess what? This one converges also by AST, which means, how did we pick up those endpoints? Because we know in a geometric setting, we don't get the endpoints ever. If it starts out as a geometric, you don't have to check endpoints. The problem was we took an integral. And when we took that integral, we spat out this 2n plus 1 in the denominator, which can have an effect. Clearly it can. Way back here, we didn't have, let's see, where am I? Good Lord. Way back here, notice we weren't dividing by 2n plus 1. So it was really simple to see. If I plug in 1, then I get 1 times negative 1 to the n. Guess what? this thing's just going to go negative 1, 0, negative 1, 0, or 1, 0, 1, 0, 1, 0 when I plug in my terms. If I plug in negative 1, I get the same thing, negative 1 to the end, which goes 1, 0, 1, 0 as I add, right? It goes 1 plus negative 1, plus 1, plus negative 1, plus 1, et cetera, et cetera. All right? When we integrate, we get extra terms because we're dividing through by those constants, right? In this case, 2n plus 1. That's pretty cool. Okay, let me show you a couple others real quick. How about this guy? I'm going to do 2 of them and then I'll be done. Let's do f of, I got to get rid of this orange. Sorry, you guys. Let's do, how about f of x? Let's do f of x. This one's fun. Is equal to the natural log of 1 plus x. I'm going to do that one. And then over here, let's do g of x is equal to 1 over 1 plus x squared. All right? Now, this one's fun. All right, check this out. Let's see what happens. If I do, let's see. It's clearly not in my geometric form. Dang it. However, if I recall something, I know that the derivative of the natural log of 1 plus x is equal to 1 over 1 plus x. Oh, now wait a sec. This is in this form, isn't it? Or close enough to it. This is 1 over 1 minus negative x, right? Which we know, because it's in this form, becomes the sum, as n goes from 0 to infinity, of a, well, a is 1, so I'm not going to write it, which is dumb, well, maybe I should write it, 1 times what? R to the n, which is negative x to the n. If I clean this up, then I get the sum, as n goes from 0 to infinity, of negative 1 to the n, x to the n. Okay, cool. Right on. Fantastic. If I pulled out my graphing calculator, it would be relatively easy to see that if this converges to this. Where? On what interval? Well, this is for x less than 1, right? Because we know absolute R for a geometric series has always got to be less than 1. Easy. Nothing to it. This is 4. All right. However, look what I got. This, the derivative of this gives me this, which gives me this, which is nice, which implies what? Well, I know that the natural log of 1 plus x is equal to the antiderivative of the derivative of the natural log, of 1 plus x dx, right? Because antiderivatives and derivatives cancel each other out, which means since this is the antiderivative of 1 over 1 plus x dx, which is equal to the antiderivative of the sum, as n goes from 0 to infinity, of negative 1 to the n, x to the n. Of course, don't forget your dx, which is equal to what? Well, let's look close. Remember, the integral of the sum is the sum of the integrals. So this is equal to the sum, as n goes from 0 to infinity, of the integral of negative 1 to the n, x to the n, dx. And we're off to the races. This is equal to the sum, as n goes from 0 to infinity, of negative 1 to the n, that's a constant, x to the n plus 1 over n plus 1, plus c. We got to include that c because it's clearly an indefinite integral. But can you see, I'm just going to stick this over here, and I'm going to say the natural log. These two things are equal, right? This, the left, is equal to that. Now, it looks amazing. God, we look so smart. We did such incredible math. No, we didn't. We took the antiderivative of x to the n. That was the hardest move that we had to make. That's the coolest part. I got to solve for the c, though. Hopefully you're seeing, no pun intended, see what I did there? If I let x equal 0, so for x equal to 0, doesn't that imply that I'm not going to make you guys suffer through this whole thing. Look, if I let x equal 0, what happens to this term? I just add up a bunch of zeros, don't I? So I get 0 plus c equals the natural log of 1 plus 0, which is the natural log of 1, which is 0, which implies c equals 0. So the natural log of 1 plus x in an absolute coup de grace is the sum, as n goes from 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. Isn't that amazing? Now, check the endpoints. Remember, we know for sure we get for free because this function came from this geometric series, right? We know for sure we get for nothing that the absolute value of x is less than 1. We know that the radius is 1. We know it's centered at 0 and the radius is 1. But we should check endpoints. Let x equal 1. Now, I'm going to do this real quick like n equals 0, infinity of, well, if I plug 1 in, what do I get? I just get 1. So this becomes negative 1 to the n over n plus 1, which does what? It converges. How? By AST. AST. So we know we get 1. How about negative 1? I won't make you suffer through it. What would negative 1 do? Well, I would get negative 1. So what would happen? Let's go up here. I am going to make you suffer through it. How about let x equal negative 1? Because the negative ones are always the hardest. Well, this would become the sum as n goes from 0 to infinity of negative 1 to the n times negative 1 to the n plus 1, which I'm going to go negative 1 to the n, times negative 1 all over n plus 1. Now, that's supposed to be in parentheses. Now, let's think about this. Negative 1 to the n times negative 1 to the n is negative 1. Wow. Dude, it's starting to look like a poorly done emoji. Using a keyboard emoji. This is negative 1 to the n plus n, which is 2n, right? Well, this is equal to just 1 because negative 1 squared is 1. 1 to the n is 1. So this whole thing turns into the sum as n goes from 0 to infinity of negative 1 over n plus 1. Which means what? Does this converge or diverge? You may be lulled down a false sense of security because of that negative 1. This is not an alternating series, ladies and gentlemen. This is not. Can you see why? It's always negative. It's going to be, first term is going to be negative 1, second term is going to be negative a half, negative a third, negative a fourth, etc., etc. Guess what? This thing diverges. Why? Now, think about this. This is a little bit cheating, and I'm going to let you cheat a little bit on this one. If you want to be exactly perfect, this would diverge by the limit comparison test. You can't call it a p-series because it isn't a p-series. A p-series is 1 over n to the p, not a p-series. All right? You also can't call it harmonic, but you can almost call it harmonic. And if you were to call it harmonic, we'll keep a dirty little secret. I would say it's okay. So you could say instead of, don't tell the other mathematicians, you could say it's because it's so much like the harmonic. Harmonic is why it diverges. So my radius of convergence for the natural log of 1 plus x is 1. My interval of convergence is what? Well, negative 1 non-inclusive to 1 inclusive. We picked up 1, but we weren't strong enough to pick up negative 1. Excuse me. Isn't that fun? Okay, one more. I got to scooch over. Let's see. G of x, and then I'll be done, I promise. G of x is equal to 1 over, what did I say, 1 plus x squared. All right? Now, excuse me. Now, this in no way looks like this, which we know is the sum of a geometric series, where absolute R is less than 1. My writing is all over the place, isn't it? However, some of you may see that this thing is really, really close to the derivative, and hopefully you will start seeing this, of 1 over 1 plus x, right? I know that the derivative of 1 over 1 plus x is equal to negative 1 over 1 plus x squared. So if I take the negative derivative of this, let me change the color of my pen. And put it in red. If I take the negative derivative of this, that would give me the negative value of this, which would equal 1 over 1 plus x squared, which is pretty cool. All right, so here we go. This is where it gets fun. We know that, let's do an implies over here. I know that 1 over 1 plus x, this function, we've already played with this, is the sum of negative 1 to the n, x to the n, as n goes from 0 to infinity, right? Because I would rewrite this as 1 minus negative x, right? Easy peasy. So, notice I have an implies here. The negative derivative of the sum as n goes from 0 to infinity of negative 1 to the n, x to the n, is equal to the negative sum of the derivative of negative 1 to the n, x to the n, right? This is as n goes from 0 to infinity, right? The derivative of a sum is the sum of the derivative, All right, now this negative is going to give you a little bit of fits, but we're not afraid, right? Because we figured it out. The derivative of 1 over 1 plus x produces a negative 1 that we don't want. So we just tack on a negative. Now that negative is going to be along for the ride until the very end. Now again, notice this, let's go into blue now. This is an x, which means that anything that ain't an x is a constant and is along for the ride. So I'm going to write negative, the sum, as n goes from 0 to infinity, of, well, negative 1 to the n, along for the ride, right, times nx to the n minus 1, right? Nx to the n minus 1, nothing to it, all right? And then I distribute my negative in there, and I end up with the sum as n goes from 0 to infinity of negative 1 to the what? Now, don't forget your negative. Had God been a mathematician, respect thy negative. This constant, this negative 1, can be put inside the sum. So I get a negative 1 to the n plus 1 times nx to the n minus 1. Isn't that delightful? And I don't have to worry about any silly c's. So this turns into 1 over 1 plus x squared. Now, again, here's the coolest part. Let me help you out. I'm not going to force you to do this. The best part is when you take a derivative of a series, you preserve radii, just like when you take an integral of the series. The cool thing, though, is that when you take a derivative of a series, even though it preserves radii, it also preserves intervals. In other words, we're not going to pick up any extra values like we did with the antiderivative, like in this case. We picked up the 1 because of the behavior, right? It was because we were dividing through by an n. In this case, we're not dividing through, we're just simply taking a derivative. So I know that the radius of convergence for this, the radius is just going to be 1, and the interval, again, the interval is just going to be from negative 1 to 1. And that's how it works, which is pretty awesome. Okay. Let's see. Are there any questions? Any problems? What can I do for you? Well, we'll address those in class. I know that this is, I know it's heavy. I know there's a lot going on, but we're going to spend some time on this, so don't panic. We'll guide you where you need to be guided, and trust me, in just a little bit, it's like we got one more section left, so at least your suffering is very short term. I know that doesn't really help at all. But anyway, relax, enjoy it. We spent a couple days on this in class. For those of you that don't have me, I don't know what your teachers are going to do, but that is what it is. So enjoy, and I'll see you tomorrow in class. Thanks for listening.